Okay, is Mithun here? Okay, Mithun, what was the doubt? What was the doubt? Yesterday you asked me something. Are you there?
Yes, sir.
Yeah. What was the doubt?
Doubt on that redox reaction as the basis for titrations, the topic in textbook, sir.
Okay, okay, fine. So we are talking about redox titration. So it's a small topic. We already know how we do titration, isn't it? Say I'm going to have something called a standard solution, right? So basically, why do we use titration for? Titration is used for finding the unknown concentration, right? I have a solution with me. I know what is that. So for example, it can be HCl, it can be any base, or it can be any acid, or it can be any oxidizing or reducing agent, right? So I have to know what is the unknown concentration of that particular whatever the thing I have to find out, right? Okay, so we have already done acid base titration, right? Say in the sense that you would have prepared a standard solution which you know the concentration, right? There is something that's called as a standard solution, right? For you would have only prepared this. Okay, so you know the concentration. Concentration is known, right? Now there is something called as an analyte, right? Analyte is the one for which the concentration has to be found out, right? Okay, so in case of redox titrations, right, both these will be oxidizing or reducing agents. Oxidizing or reducing agents, right? Okay, so for example, right, for example, I need to find, right, what is the unknown concentration of KMnO4. I know KMnO4 is an oxidizing agent. Okay, I have to know what is the concentration for I have a solution of KMnO4 and I need to know what is the concentration of this. Okay, so please understand, you have two things there, and if you've done things in your chemistry labs, you would have done it like you will have something called as a pipette, right, and you will have something called as a burette, right? Okay, so from the standard solution, right, say the standard solution is going to be something. Standard solution can be anything which undergoes oxidation, right? Standard solution is anything which undergoes oxidation, right? Okay, so from the standard solution you take the required volume, right? You take the required volume and you put it in the titration flask, right? So you are going to have set up something like this. So this is my titration flask. Okay, so into this I will be putting the standard solution, not say some volume of standard solution which for which the concentration is known. So there is some standard solution here, right? Now on top of this, now you will put your burette, right? Now this burette is going to have some kind of tap, right? So into this you put your unknown KMnO4. Okay, right, now this burette has a small tap, right? So you'll open it, right? Again, in case of titrations, you'll put something called as indicators, right? So indicators are used to indicate whether the reaction is completed or not, right? Now in this case, so for example, in your acid base titration, you would have used phenolphthalein, methyl orange, methyl red, right? So all these indicators will change their colors, indicating that the reaction has completed, right? So what will happen if you just keep on opening? For example, if this was HCl and this was NaOH, right? You will add phenolphthalein along with this, right? So NaOH with phenolphthalein will be pink in color, right? So now if you open the tap slowly, 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 the pink color will start decreasing. Now at a point of time, this pink colored solution will turn colorless. At that time, you'll stop it. That is the end of the reaction. Okay, so in this case, I don't have to use any indicator. Why? Because my KMnO4 itself is going to act as the self indicator. Right now, self indicator means that it's already, I know, is purple in color. Right, so you will see this solution is there, it's going to be colorless. Okay, and obviously in the burette solution you have KMnO4, which is going to be purple in color. Okay, right, now what you do, you just open the tap slowly, 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 the reaction will happen. Now drop by drop by drop, KMnO4 will be adding to this, and this solution will keep on getting oxidized, right? Now at a point of time, what will happen? Say assume that this is going to be an acidic medium, right? You should add little amount of acid also to this, little 1 or 2 drops of acid also to this. Okay, So what you have to understand is in acidic medium, MnO4 minus will form Mn2 plus, right? Now this Mn2 plus will be black in color. Okay, so when you see that the reaction is completed, this solution would have turned black in color. Okay, that's the indication. Now, obviously, you know how much volume of this KMnO4 would have been used for this reaction, right? Now, depending on the stoichiometry, say I have, I'll reuse this M1V1 is equal to M2V2, but I cannot do it directly. Now, this happens when I have equal number of moles required, right? Say if something like MnO4 minus required 5 Fe2 plus, say these two are the reactants, right? Now, how will you write? Now, if at all this one is for KMnO4 and 2 is for Fe, you will put into 5 here because I know M into V will give you number of moles. So for 1 mole of MnO4, I require 5 moles of this, right? So I know what is the molarity of Fe2 plus solution because I only prepared it. I know the volume because I took it in the pipette and put it here, right? And I know what is the volume used for a KMnO4 because it is coming to the burette and I'll be able to measure it. So this value can be found out. Okay, this is what is called as redox titrations. Understood? Mithun, is it okay?
Actually, in NCERT, it was written something as own indicators, indicates, dissolves the other indicators, and if it dissolves iodine, it changes the.
Exactly. So that's what I'm talking about. You're talking about this standard solution, right? This standard solution I took is Fe2 plus. You can take it as iodide. Iodide will become iodine, mean I minus will become I2. So in that case also, again, you don't have to do anything. Self-indicators is what is going to work because KMnO4 is already purple in color. That purple color will be changed to some other color during when the reaction gets over. That's it. How I don't understand what you're telling. Like in one indicator dissolves another indicator. I think I don't know what you're speaking about. Check it properly. But whatever I'm telling you
No,
is what
sir.
is it?
In case of copper and zinc, if we place a strip of copper and zinc sulfate, what will happen, sir?
If I put a strip of copper and zinc sulfate, nothing will happen.
No, sir. If you put a strip of zinc in copper sulfate, what is the
Then
reaction, sir?
displacement reaction will happen. Zinc plus copper sulfate will give me zinc sulfate plus copper normal displacement reaction because zinc is more reactive than copper.
No, sir. Which is the indicator, sir?
That time, what is an indicator? Oh, no, that time again, copper sulfate itself is an indicator. No, copper sulfate will be blue in color, blue colored solution. Correct. Now, when the reaction is over, what you have is only zinc sulfate. Zinc sulfate will be colorless. So in that case, it will become a blue colored solution to a colorless solution. Again, I don't have to use any indicator there. It's going to act as self-indicator again. Understood?
Sir.
Okay. So like only if you don't see any color change, then you have to go for any indicator specifically, right? But in the reaction itself, something is colored, right? Then you don't have to go for any indicator. That itself will indicate the reaction getting over.
Sir, you said zinc will be colorless, no, sir?
Yeah, zinc sulfate will be colorless. Yes, tell me.
If I pass hydrogen sulfate in it, then the colorless solution will change into black color solution. Can I say H2S as an indicator, sir?
Not no. In this particular case, what you're telling, I don't have to use. That's what I'm telling. CuSO4 is there. Copper sulfate is blue in color. When I add zinc to that, that solution is going to become colorless. I don't have to use any indicator. Hope you understand what I'm trying to say.
Okay, sir.
Okay, but if at all, if it is not copper sulfate, if at all say it was some other thing, right? At that time, maybe if I pass H2S gas, it is going ZNS. ZNS will, I think ZNS will also be colorless only. I don't think it is going to work. H2S gas passing, I don't think so how it is going to work. Okay, so bring like maybe you send that picture, whatever the page you're talking about. Maybe I'll look into it, whatever you're saying.
Okay, sir.
Okay, fine. So yes, that is about redox titrations. Okay, right. So we were seeing hydrocarbons. We have completed almost everything. Alkenes, everything is completed. in alkenes alone, there is just one more reaction I left out. Okay, so that we'll see. So for example, if I had CH3, CH double bond C, I'm going for, basically I'm going for, okay, fine, we'll see. So when I directly put HBr, right, I know what is going to happen. You have to follow Markovnikov's rule, right? So you will get a product like this, right? You'll get a product like this, Markovnikov's addition, right? But if I don't want this to happen, I want Br here only. I want the Br to come here only and not here, right? Is there any way? Yes, there is a way, right? Now we'll see how to go for anti-Markovnikov's addition of HBr. Okay, anti-Markovnikov's addition of HBr, right? Okay, so what we have to do is, if I take this compound, right, I have to add HBr in the presence of a peroxide. As simple as that. Okay, in the presence of a peroxide, right? Now what is going to happen is, you will see that I'm going to have anti-Markovnikov's addition of HBr. You see, Br is getting added to the less substituted carbon atom. Okay, right. Now this is very easy. Now you have to remember that if I just put HBr, it is going to become Markovnikov's. If I put HBr in the presence of peroxide, right, you will see that it is going to be what is that? Anti-Markovnikov's addition. Now what you have to understand is the mechanism, right? How this happens, right? Okay, so we'll see that. Now please understand, if I just put HBr not in the presence of peroxide for this, tell me what will be the intermediate form for this reaction. What is the intermediate form? What is the intermediate? For this reaction, what is the intermediate? It can be only three: carbocation or carbanion or free radical. What is going to come here? Okay, fine. Now in this HBr addition, yeah, someone is saying something.
Carbocation.
Yes, carbocation. Right, easy, right? So first what happens? This is an electrophilic addition reaction. Electrophilic addition means first the electrophile comes here. The electrophile is H plus. So when H plus attacks this carbon, you will form a carbocation on this carbon, and then the Br minus attacks this carbon, forming this compound. Right. Now here in this case, free radical is going to be an intermediate. Okay. Right. So we'll see how this is going to happen. Right. First step in this, right? Say I'm going to use a peroxide, isn't it? So it can be any normal hydrogen peroxide, or it can be any organic peroxide. Organic, see, peroxide means I'm going to have this OO linkage. That is what is a peroxide. Now it doesn't matter what you're going to put here. You can put HH, or you can have ROOR, right? This is my organic peroxide. This is hydrogen peroxide. Okay, right. So what is going to happen is this ROOR, or say HOOH, or hydrogen peroxide. First step is this bond undergoes homolytic cleavage. Okay, this bond undergoes homolytic cleavage, right? So what will happen? I'm going to form 2 moles of RO dot, free radical. Okay, now next step is this RO dot is going to react with HBr. Okay, this RO dot reacts with HBr, and it is going to abstract a H dot. It is going to abstract a H dot. Can I say it is going to form ROH plus Br dot? Okay, it is RO dot is formed here first from the homolytic cleavage of this OO single bond peroxide linkage, right? So it will form RO dot, and this RO dot will abstract the H dot to form ROH and Br dot, right? Okay, what is the next step? Next step is, so when I take this compound, right, now the Br dot comes. Now the Br dot comes. Now you have two possibilities. right? What is the first possibility? Now say this Br dot can attack this carbon or it can attack this carbon. Correct, right? So we'll see how is it going to happen, right? So if this Br dot is attacked, it is going to attack any of these two carbon atoms. Obviously, the pi bond here has to undergo homolytic cleavage. Is it not? Right? Say if this undergoes homolytic cleavage, right? So obviously, for example, if this attacks here, right? If this attacks here, and obviously this radical and that is going to form a bond. So what will be remaining? It will be, I will have CH3, CH dot, CH2, Br. Okay, again I repeat, this you would have understood. Here I'm going to have homolytic cleavage of this pi bond, and when the homolytic cleavage happens, the Br dot can attack any of these two carbon atoms. I'm taking the first case that it is going to attack this carbon atom. I'm going to have this radical getting formed. Right. So what will be the next step? Or say what will be the other step? CH double bond CH2. Again, homolytic cleavage. Br dot is going to come. Now this Br dot attacks here. For example, you will form CH3, CH, Br, CH2 dot. Right? Okay. Now, what kind of radical is this? Primary, secondary, tertiary. What kind of radical is this? First one. What kind of radical is this? After so many classes, are you still going to think what kind of radical is this?
So it's a secondary radical.
Yes. Okay, so you see the carbon having the radical is attached to two other carbon atoms. So this one is the secondary free radical, and this one?
Primary, sir.
Right. So this carbon having the radical is attached to only one other carbon atom. This is primary. Okay. Now, tell me, primary, secondary, tertiary radicals, arrange them in the order of stability. Which is going to have more stability?
Secondary, sir. Tertiary followed by secondary followed by primary.
Correct. Right. So you'll easily understand that the order of stability of free radicals would be tertiary greater than secondary greater than primary, just like carbocations. For carbanions, it will be ulta. Right. Oh, so okay. So what is going to happen? I have a secondary free radical. I have a primary free radical. Obviously, secondary is more stable. That only will be formed in more amount. Right. So out of these two, this will be formed in higher amount. So what is going to happen? I will have CH3, CH2 dot, CH2 Br. Now it is going to take one more molecule of HBr so that this can abstract a H dot. This H dot comes and attacks here. So it will form CH3, CH2, CH2 Br. This is how the anti-Markovnikov addition reaction happens. Okay, so what kind of product you ended up with, right? Since that is formed in majority, that will only take the H dot from HBr to go to form this molecule. Anti-Markovnikov addition, right? So that is the use of peroxide. Peroxide, if you use, it is going to initiate the free radical mechanism, right? If you don't use peroxide, carbocation will be the mechanism, and that time you're going to get Markovnikov's product. Okay, right. So now if you ask me, sir, if I put HCl in the presence of peroxide, will this reaction happen? Or say if I put HF or HI for this reaction, it will happen. The answer is no, right? So what I'm trying to tell you is, if you have CH3, CH double bond CH2, if you put HCl in the presence of peroxide, still you will get only Markovnikov's product. Right? See, still you are getting only Markovnikov's product as the major product. Okay. Now, how will I be able to answer this question? Now, I'll be able to answer this question if I look at the mechanism little carefully. Okay. Now, what I have to understand is, people, like in case of HBr, I have this HBr bond, and in case of HCl, I have this HCl bond. Right. Now, if I make it react with RO dot, it is going to come from the first step. Hope you take it down. You will easily form the Br dot. So this also has to undergo homolytic cleavage. Correct. Right. Now this HCl bond cannot undergo homolytic cleavage because this bond is stronger than the HBr bond. Okay, this bond is stronger than the HBr bond. Okay, so that is the reason why from this Cl dot cannot be extracted. Same goes with HF. HF also same thing. HF is still more stronger than HCl. Right? So definitely you cannot do it. You cannot form F dot from this particular HF, or say HCl, you cannot form Cl dot. But from HBr, you can form Br dot because this bond is little weak. Right? Then you can ask me, sir, I can easily do this, right? I have HI. This bond is weaker. Then I should be able to easily do it. But still it doesn't happen. Why? Because from this, if you form the I dot, this I dot is very, very, very unstable. This I dot is very, 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 very unstable. And that is the reason why if you just go for CH4 in the presence of I2 bar H nu, if I put Cl2 bar H nu, free radical substitution. Br2 bar H nu, again free radical substitution. But if I put I2 bar H nu, there is no reaction. Why? Again, the same reason, because I dot is unstable. Right? Okay. So why HCl and HF doesn't give is because of the higher bond strength of HF and HCl bond. And why HI doesn't give anti-Markovnikov is because I dot is unstable. Okay.
I have a doubt.
Yeah, tell me.
So we can conclude that weaker acids work in anti-Markovnikov.
Weaker acids?
Yes, sir. Weaker acids only work in anti-Markovnikov.
Yeah, we can consider it like that. But here we are not even talking about acidic strengths, right? There is no one giving me H plus. There's nothing, right? It's all about homolytic cleavage. All we have to speak about is the strength of the bond. Yeah, but what you can conclude here is yes. But again, HI is the strongest acid. HF and HCl doesn't give, and HBr gives. So there is no trend like that. I cannot generalize the trend with respect to acidic strength. No, we cannot do it.
Okay, sir. Understood.
Okay, right. So anyways, so mechanism, if you can remember the mechanism, very, very good, right? But again, I don't know what your school is gonna, how your school taught you. And I definitely know for sure that mechanism will not be there in your book. Okay, so I don't know, and I don't know how many of you are taking notes. Okay, so this and all are going to be very, very important. Maybe not with respect to marks, but knowledge point of view, very, very important. Okay, so that is about your anti-Markovnikov addition. Right? Okay, fine. Now we'll move on. Okay, fine. So next what we'll see is benzene reactions. Okay, now benzene I know is this. Easy, right? Now there are so many type of reactions. There's only one type of reaction which benzene can undergo, and in that itself I can have so many types of the particular reaction. Okay, fine. So benzene, what kind of reaction it will undergo? If you ask me, it is going to undergo electrophilic substitution reaction. Right? My benzene will undergo electrophilic substitution reaction. Okay, right. So I think from the name itself, you can understand what I'm trying to say. Right? Electrophilic substitution. So what do you mean by that? One electrophile in the molecule is replaced by another electrophile. Nucleophilic substitution means one nucleophile is replaced by another nucleophile. Normal substitution means what? One thing is substituted, replaced by some other thing. Now, specifically in this case, it is going to be an electrophilic substitution. One positive charge is replaced by another positive charge. Okay. Now, in benzene, what you see is there is nothing. There is nothing. Only hydrogen atoms are there. All 6 things contain 111 hydrogen atom. Right? So obviously the only thing which I'll be able to replace is H plus. Right? So if I want to write a reaction, say that I have this hydrogen, if I put any electrophile, E plus. E plus is any, I'll tell you what are the electrophiles, what are the reactions possible. This is a general reaction. Okay, so if I put any electrophile, I can form this E will come here and I'll replace the H. Okay, so this is what is called as your electrophilic substitution reaction. Okay, now this is very simple. What we have to know is the mechanism. Okay, what you have to know is the mechanism. We'll see how this reaction happens. Okay, so what is going to happen is, okay, say I'll take this hydrogen, right? Fine. So first the electrophile comes, right? Say now obviously say assume that this is a positive charge. Obviously I have the pi electron with me. Say assume that this pi electron attacks the electrophile, right? Obviously this carbon atom is what is going to attack the electrophile. So what will happen is, can I say I already have hydrogen and now this carbon atom has attacked the electrophile, right? But if you look at this carbon has lost electrons, right? Can I say there will be a positive charge here, right? Okay, now what are the other things that are present? This one. Okay, now resonance structures are going to happen, right? Now resonance structures are going to happen, right? So what will be the next step? Say now as first step would be this coming here, making a bond, right? Say if I write it at the top, right? I'm going to have a bond here. Now see, this carbon has lost electrons. So now this will have a positive charge and there is a bond, there is E, there is H. Right? Now what will be the next step? This will come here. Right? Now there is a bond here, there is a bond here. Now you see this carbon atom has lost electrons. So you'll have a positive charge here and there is a H and there is a okay, there is a E and there is a H. Okay, now the last step is very easy. What is going to happen is, you see this hydrogen is going to come out as H plus and this bond is going to come here, make a double bond. That's it. Okay, so from this I remove H plus and the single bond I had, the CH single bond is going to come here, make a double CC bond and this positive charge is gone, right? So you'll see that you will have bond here, bond here, bond here with only the electrophile plus H plus. Okay, see how we did it? It's very easy. First step is this pi bond attacking the electrophile. That means basically what you have to, or you can understand it like, if I break this bond heterolytically, I'll form a negative charge and a positive charge, and this negative and positive attracts. Right? Okay, so you will have a positive charge here. Next step is resonance. Now this bond will come here. So now you will see there is a bond here. Obviously this carbon would have lost electron, so positive charge, right? And then the next step would be attacking this. So now this carbon will have the positive charge. And the last step, H plus is going to come out and the single bond I had there is going to come back to make a double bond here with only the electrophile. Okay, so this is how any electrophilic substitution reaction happens.
So there's no specific place we'll target, right? It can be
Doesn't matter.
anywhere.
Wherever you put the electrophile, the same resonance structures will continue.
Okay, sir.
Where you're gonna put it. Right? Okay, fine. So next thing, right? Now you understood how the mechanism works. Now you have to understand what and all can be the different kinds of electrophiles I can have. Right? Fine. So that basically we're going for the reactions. Right? Okay. So please take this down. I'll just give you one more minute, or if you're taking it, don't tell me, I can drop this part.
Done, sir.
Okay. Right. So there is something called as Friedel-Crafts reactions. Okay, Friedel-Crafts reaction, right? So under this, say first one I take is Friedel-Crafts alkylation. Friedel-Crafts alkylation. Okay, fine. So now remember, for any Friedel-Crafts reaction, you are going to obviously you're going to use something along with the Lewis acid, right? You're going to use a reagent. One reagent will be there, and along with that, you will use one Lewis acid. Okay, so this Lewis acid is going to help me create the electrophile. Okay, this Lewis acid is going to help me create the electrophile. Okay, so what can be Lewis acids? Generally, I go for FeCl3, or I can go for AlCl3, or I can just put Fe, right? So these are all these are generally the mostly you will be using only AlCl3. Okay, so these are all the different kinds of Lewis acids which you can use to produce the electrophile. See, if I just have the nucleophile, nothing will happen. I have to produce the electrophile, right? So that electrophile produced is taken care with the help of these Lewis acids. Okay, so not only in this reaction you will have alkylation, acylation, bromination, chlorination, all these things, right? In all these things you will have one reagent along with the Lewis acid. Okay, fine. So now, for example, if I have to go for alkylation, I have a benzene ring, right? Now, what I have to go for is RCl. R is any alkyl group. R can be methyl group, it can be ethyl group, right? RCl in the presence of AlCl3. RCl in the presence of AlCl3. Okay, so what is going to happen is you are going to see this RCl reacts with AlCl3 first. Okay, now this is a Lewis acid, correct? So what do you mean by Lewis acid? It will be able to accept a lone pair of electron, or it will be able to accept some more molecules, correct? So what is going to happen is this Cl minus attacks this. So what will be remaining here will be R plus AlCl4 minus. AlCl4 minus. Now how this is getting formed is because this is a Lewis acid, it still has an empty orbital, so that can be formed. So what you see here is R plus, that is the electrophile, right? So now what will be the product now? You will easily see the product is R coming here. H plus, maybe there is a hydrogen here that is replaced by whatever the alkyl group is. If at all you use CH3Cl in the presence of AlCl3, you will get CH3. Toluene is what you will get. Right, so again you can understand how this AlCl3 or the Lewis acid is helping me to produce the electrophile. Like this only it will help.
I have a doubt. This RCl heterolytic cleavage takes place.
Yeah. First the heterolytic cleavage takes place, then the Cl minus is accepted by AlCl3 to form this.
Okay,
and then
sir.
what is remaining is R plus.
I understood, sir. Thank you.
Okay, right. So that is your Friedel-Crafts alkylation. Right. Okay. Next reaction is Friedel-Crafts acylation. Right. Please understand, acyl is something related to C double bond O. Okay, acyl is something related to C double bond O. Right. So I am going to introduce a C double bond O to this benzene ring. That's what I'm trying to do. Okay. So very simple. I have the benzene ring with me. Right. So if I go for RCOCl, this is what is called as acid chlorides. Okay, so when I have something called as acid derivatives. Okay, I know carboxylic acid is RC double bond O OH, right? This is what is my carboxylic acid. Instead of this OH, if I put something else, some Z, okay, those are what are called as acid derivatives, right? So this can be chlorine, this can be amine, right? It can be some other thing. You will study about them when I go for higher level, when I go for 12th class. But for now, please understand that one of the acid derivatives possible is this RCOCl, acid chlorides, or acyl chlorides. They are called. You can take this name, acyl chlorides or acid chlorides. Okay, RCOCl. Again, this R can be anything. It can be CH3, it can be C2H5, it can be anything, right? Obviously, since it is Friedel-Crafts, I have to use my AlCl3. Okay, now exactly same thing. What I told you here is going to happen, but instead of RCl, you have RCOCl, right? So if you look at how the reaction is going to happen, right? So I have this RCOCl. Now this is going to undergo hydrolytic cleavage, and I'll have the AlCl3. So you will have RC double bond O plus AlCl4 minus. Again, the Cl minus will be accepted by AlCl3. So what will be remaining is RCO plus. No issues, right? So next I can easily go for C double bond O R. Now positive charge attain positive charge is possessed by the C double bond O, right? The carbonyl carbon. So that only will attack the benzene ring. So it'll form benzene ring with C double bond O and R. So I have introduced a C double bond O in the benzene ring. Okay, similar, exactly similar, except that instead of RCl, I have RCOCl. Same thing, right? Okay, next
So I
is
have a doubt.
yeah.
This AlCl4 minus, what will happen to that? So it'll just remain.
AlCl4 will remain the solution. So
It won't interact with benzene.
I'll tell you how is it happen. So basically, this AlCl3 will be the form of an aqueous solution because this is soluble in water. Okay, so this will remain in the aqueous phase, but benzene will not be dissolving in water. It will be still in the organic phase, right? So this AlCl4 and this are not going to interact because they're in two different phases. One in organic phase, this is going to be in aqueous phase. So no reaction will happen.
Okay, sir.
Understood?
Yes,
Right?
sir.
Okay, cool. Now next is Friedel-Crafts halogenation. Right, halogenation can either be Cl or Br only I can do. Right, how will I form other types of fluorobenzene, iodobenzene, those things we'll see in 12th class. There are other ways of doing it. Okay, fine. So halogenation. So again, I have the benzene ring with me. Right. In this case, I have to go for X2 in the presence of AlCl. Right. Again, X can either be Cl or it can be Br only. Either Cl2 or Br2. Right. Now, same thing will happen in this case. Say if I take XX bond. Okay, if I take the XX bond, now in say first this XX bond undergoes heterolytic cleavage, right? And obviously I'll have the AlCl3, and this X minus is going to attack the AlCl3, right? So what will be remaining is X plus, for example, Cl plus Al XCl3 minus. Basically, if it was Cl minus, it will again become AlCl4 minus. If it is a Br minus, then it will become AlBrCl3 minus. Right? In general, I wrote it as AlXCl3 minus. And what will be remaining is this X plus. Right? And that's it. You will see the same mechanism what I told you earlier, and I will form the halobenzene, bromobenzene or chlorobenzene. Okay, right? So these three are what are my Friedel-Crafts reaction. Friedel-Crafts alkylation, acylation, halogenation. That's it. Okay, right. So other than the Friedel-Crafts, right, I have one more reaction, not Friedel-Crafts, but some other way I'm going to do it. Okay, that is
One is copy halogenation.
yeah. We take down, dropping the down part, so up part only.
Done, sir.
Yeah. So the last reaction is my nitration reaction. This is not Friedel-Crafts. Okay, for Friedel-Crafts, I have to use a Lewis acid. I'm not going to use any Lewis acid here, right? So directly, I'm going to put NO2 group into the benzene ring. Nitrobenzene is what I'm going to form. Nitration means nitrobenzene is going to get formed, right? Now, easy. I have the benzene ring. Now what I have to use is a mixture of HNO3 and H2SO4, concentrated HNO3 and concentrated H2SO4. Okay, now this particular thing is what is called as your nitrating mixture. Right, this particular thing is what is called as your nitrating mixture. Right, and you don't have to worry how this happens. Somehow this HNO3 and H2SO4 produces NO2 plus. Okay, this HNO3 is going to produce NO2 plus. Nitrating mixture produces nitrite ion, NO2 plus. Right, and that's it. If I produce the NO2 plus in the benzene ring structure, you will introduce an NO2. That's it. Okay, so you'll introduce a NO2. Okay, right. So these are the reactions. And what I want to know, have you ever heard this term ortho para directing, meta directing? Did they teach you all this?
Yes, sir. It taught about ortho para.
Okay, fine. So we'll see that also. Cool. So these are the different types of reactions you can have for benzene. Okay. Now you are seeing only mono substituted products, either one NO2 or one Br or one CH3 or one acyl group. Only one things you are seeing. Okay, right. Now what if I have to go for di substitution? Right? What if I have to give one NO2 and I have to put a CH3? Okay. Now at that time you will think, right? For example, okay. Right. Say I have this, for example, NO2, right? And if I go for CH3Cl in the presence of AlCl3, okay. Now you have 3 positions in which this CH3 plus can attack. Say this is the first position, second position, or third position, or again 1, 2, 3 will be same. That side also if you go, right? Either this or this position you can attack. Right. Now how will you decide? Right, now if you remember how to write the resonance structures for nitrobenzene and different kinds of molecules, right? I told you electron withdrawing groups will have one kind of resonance structure, electron donating group will have another kind of resonance structure, plus R and minus R what will be there, right? So NO2, okay, now in this case if you understand, right, you will see that the product will be CH3 here. CH3 here. Now this, okay, remember, okay, first I have to give you this. Okay, fine. So please understand this first position is what is called as your ortho position. I'll represent it as O. Okay, first position is what is called as your ortho position, right? Second position is what is called as your meta position, denoted by the letter M. And lastly, third position with respect to this is what is called as your para position T. Okay, ortho, meta, para. Right. So that is what they say. Now what you see is this CH3, which is incoming CH3 plus, right, is directed towards the meta position. Right. So that is why I call NO2 as a meta directing group. Okay. And if at all you see, for example, I had phenol. Okay. And I go for this alkylation, or say if I go for nitration or anything, HNO3 plus H2SO4, whatever it is. Now you will see that I have OH, NO2 here plus OH and NO2 here, right? Now what you saw is that OH, if I have in the benzene ring, the incoming electrophile, whatever be the electrophile, right? The incoming electrophile is directed towards either ortho position or para position, no meta product is formed. And in this case, only meta product, no ortho para product is formed. Right. So if you have, whenever you have groups which are going to do this, they are going to be called as ortho-para directing groups, right? And when you have NO2 directing your metal group to your meta position, these are this particular NO2 is going to be called as meta directing group. So directing means the ink already one electrophile is there in the benzene ring. That electrophile is going to decide if there is a second electrophile, which position it will go. Right? There are only two positions. One is ortho and para together. That is that they are teamed up. Right? The other one is meta. Now, how do we decide, sir? Right? How do we decide? You just look at the resonance structures. Then you will easily able to understand. Okay, right? So we now understood what do you mean by meta directing, what do you mean by ortho-para directing, but what we don't know, how is it happening? That we'll see now. Okay, right. Fine. So maybe if you're taking this down, I will rub this part. Okay. So guys, if I want to give you a trick, right? So any electron withdrawing group, okay, any electron withdrawing group will give me minus R effect because it is going to take the pi electrons from benzene ring, right? Now those will always be meta directing, right? And whenever I have electron donating groups, which will give plus R effect, those will be ortho-para directing. Okay, now please understand electron withdrawing groups examples can be NO2 if I have C double bond O in the benzene ring, right? So these are the things which are going to be meta directing in nature, right? And electron donating groups, if you have OH, if you have CH3, right? Or if you have NH2, right? Or if you have any chlorine bromine, I can just write X, any halogen, right? All these things, please understand, all these things are going to have lone pairs on them, and this doesn't have lone pair, but this does it by hyperconjugation. Hope you remember, right? Okay, and this also has a lone pair, this also has a lone pair, right? So all of them will be electron donating groups, right? And whenever you have NO2 or C double bond O, they will take the first resonance structure from the pi bond of the benzene ring. Hope you remember the resonance structures. Okay, so anyways, now I'll give you two structures, one for ortho-para, one for electron donating and one for ortho-para, one for electron withdrawing. We will see how this particular thing happens. What is the time? Okay, I'll be able to complete it. Okay, right. So we'll take two examples. Maybe we'll take nitrobenzene as one example, right? And I will take maybe say OH, well, that's what we took as an example, right? But any electron donating group, any electron withdrawing group, mechanism is same. Okay, I'm just taking two examples so that you'll understand how this particular thing happens, right? Okay, now say I take first your NO2 nitrobenzene. Okay, now if I take nitrobenzene, what will be the first step? The first step would be this attacking here and this bond being broken. Correct. Okay. So I will have double bond NO minus this. Can I say this carbon would have had a positive charge, and this all be the next step. This will come here. So I have double bond N O minus coordinate bond, a bond here and a positive charge here, and this will come here. Right, what will be the next step? This will be the next step, right? So double bond N O minus this one. So can I say there'll be a bond? There'll be a bond here. There'll be a bond here. Now this carbon would have got the positive charge, right? Now the last step is this will come here and this will come here, and you will see that you have N double bond O minus this thing, and I have a bond here, and a bond here. Okay, fine. So this we already know how to draw the resonance structure. Now what I want you to see is if I'm going to subject this particular nitrobenzene to a reaction, electrophilic substitution reaction, right? Now please understand, electrophile is going to go for a site which has high number of electrons, or wherever I'm going to have highest negative charge, right? Those positions only I am going to go for, those positions only that electrophile will attack. Right. Now, what I see from the resonance structure is that there is, in the benzene ring, there is no negative charge. There is only positive charges. Right? Positive charge here, positive charge here, there is a positive charge here. There's literally no negative charges getting formed. Right? So that's the reason why my electron withdrawing groups are going to be called as deactivating groups. Why is it deactivating? Because electrophiles require negative charges. But in the resonance structure of these nitrobenzene, which is an electron withdrawing group, I don't see any negative charge. I see only positive charges. Okay, and see, but still the reaction will happen. Maybe it is going to be a very slow reaction, right? But still the reaction will happen. There's no doubt about it, right? Now, again, even though I have positive charges, I have to choose a position which has, I would say, at least lesser positive charge. Is it not? Right? So I don't have any negative charge. So what is the next thing I'll check for? I will check for the places where I don't have positive charge. At least that will work for me. Right? So what do you understand? Say this is my ortho position where I have a positive charge. Here in this case, you see there is a in the para position I have a positive charge, and you see okay. Now in this case, you see in the ortho position you have a positive charge. Where I don't have positive charge is in the meta position, the third position. You will never see any positive charge coming, right? So the electrophile will choose to attack this particular meta position because I don't have positive charge or positive charge there. Okay, you should not like negative charge is found in meta position. No, only positive charges are formed in the resonance of nitrobenzene, but those positive charges are formed at ortho and para positions. In meta position, I have no positive charge. So at least that is since I have only positive charge, that is why I'm going to call it as deactivating group. But still, the reaction will happen at the meta position. The incoming electrophile will choose to go to the meta position. Okay, right. Now, if you look at any okay, obviously electron donating groups are going to be called as activating groups because they are going to activate the benzene ring towards electrophilic substitution. Because in the benzene ring, because of the resonance structure, I'm going to have negative charges getting formed. I hope you understand how, right? If you look at the resonance structure, you'll understand. This understood everybody. Why is it going to be meta-directing?
Yes, understood.
Okay, right. Now, we'll just take a resonance structure for any of the electron donating group and we'll try to understand why they're ortho-para-directing. Now, what do you predict is that I am going to have negative charges in ortho and para position. Anyways, I'll prove it to you. Right. Say if I take any electron donating group, say I have OH or NH2 or Cl or CH3, whatever it is. So I'm going to start with this. Now this will come here. This will come here. Double bond OH plus. There is a negative charge. See, because the bond has broken like this. Right. What will be the next step? This will come here. This will go here. Double bond OH plus. Now there is a bond here. There's a negative charge here, and this will come. What will be the next step? This will be the next step. OH plus. There is a negative charge here. Bond here, and a bond here. And the last step would be this coming here and this bond going back. Anyways, that is okay. Right. Now see where and all you form the negative. Now, first of all, you form the negative charge. That's the first thing. This is going to activate the benzene ring towards electrophilic substitution because for negative charges and positive charges will attract. Very simple. In that case, you don't see any positive charge, sorry, negative charge. Right. So now the next question is where and all I'm going to have high amount of positive charge, which positions, those positions only the electrophile will prefer to attack. Right. Obviously, you see ortho position, para position, ortho position. Right. So according to the resonance structure, I am able to form negative charges only at ortho and para positions. And that is the reason why the incoming nucleophile will choose to attack any three of these positions only. because there only I have negative charge, right? That is the reason why any electron donating group will be an ortho para directing group, and it is also going to be an activating group for a benzene. And whenever I have electron withdrawing group, it is going to be meta directing, as well as it is going to be a deactivating group. That's what you need to understand. Okay, so that's it. We have completed the chapter. Everybody understood this?
I have a doubt. How do you know
Yeah.
to join in the ortho position or para position, sir?
Oh, you're asking among ortho and para, which
Yes,
will more?
sir. Yes, sir. Yes, sir.
It depends. Actually, it depends on temperature. Okay, so if at all you want to know, I'll tell you. At lower temperature, ortho is higher. At higher temperature, para is higher. Right now, if at all you ask me, sir, why? Again, it's too much level for you, but still, I'll tell you there is something called as thermodynamic control and kinetic control. Okay, so based on that, we'll look into it. But again, don't worry about it. Right? If at all you want to know the answer, you can know the answer. Low temperature, ortho position is favored. Higher temperature, para position is favored. More than this is not. Even if you tell you, you'll not understand. That's the point. Okay.
Okay. Understood.
Right, but in general, you don't have to worry about it. Nobody's going to ask you this question. Generally, if they ask you, it is generally going to be only there will be almost 50-50%. Almost. That's what you need to tell them in school or in your the school exam. They ask you, and there is not going to be much partiality.
Okay.
Right? Okay, fine. So we have completed the chapter. Right. So as discussed, tomorrow you will be preparing group 1 alone and coming. Right, and I don't know how many of you are there, how many of you will be there, how many now itself we have only 3. Okay, right, so maybe only if even 2 of you are there, right, I will conduct the quiz, right, or maybe, but if only even if one of them is there, I don't know what will I do, but at least if 2 of them are there, right, I will conduct the quiz. Okay, and so please tomorrow prepare group 1 and come. I will just it can be MCQ or it can be any recent type question. I'll ask you a question and ask you why that happens, right? So all those things. You just study your NCERT book and come. Nothing else. I'm going to ask just from the book. Book means not your book back exercises, from the chapter, whatever is there, right? So from top to bottom, just study your group 1 alone and come. Okay, and ask from anywhere in the book. Only from the book, not anything extra. Okay, fine.
Sir.
Yeah, thank you guys. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.